or, okay, Jan, or Jiren. Got the rest. Okay, today we are going to talk about the Maxwell-Boltzmann distribution. Now, we're not going to go over how the Maxwell-Boltzmann distribution is developed. That's a little above our level. But what we're going to do is look at the things we can determine from it. Now, you'll notice this figure is a little different than the one that you had on Flip Friday. It shows where the average speed is, as well as the RMS and the most probable. And we're going to go through and see how we can determine what the values are for the most probable speed, the RMS speed, and the average speed if I have a gas that has this Maxwell-Boltzmann distribution. This Maxwell-Boltzmann distribution is calculated to be the distribution of speeds you'll have if you have an ideal gas and just having those collisions between atoms. You might, grab one of those. You might kind of naively guess that you should have all the same speed, but that wouldn't make sense because when you have things colliding with each other, each time you have a collision, you're going to have the speeds adjusted. So they're not going to adjust so they all have the same speed, because if they all had the same speed, you would have collisions and have changes from that situation. So this is the distribution that they will reach after having a lot of collisions. So this equation here we saw before for the distribution. Now, to understand this distribution a little better, this distribution is telling us about the probability. Here, grab one of these sheets of paper on the desk. It's telling us about the probability of a single molecule having a speed within a range. So if you want the probability of a molecule having speed between v and v plus dv, that probability is this function dv. In fact, we call it a probability density because it's a probability per a small amount of velocity. Now, when you look at this, we see this multiple places in physics, and it may seem a little odd. Why do I have to have the probability density? Why do I have to have the probability per some small range? And the answer to this you can come up with logically real quickly. Let's say that I go to an infinite number of decimal places, and I say, what's the probability of a molecule having this exact speed? If I go out to infinite number of decimal places and say, what's the probability of a molecule having this exact speed? What are you going to come up with? 0, right? You would have 0 for your probability everywhere if it was just the probability as a function of speed. You have to have the probability density. What's the probability of this particle having a speed plus or minus this amount that allows you to have a finite answer? And so that's why we have to have the probability density, the probability per some small infinitesimal dv. Now, it's still infinitesimal, but it exists. Whereas if I was saying this exact speed, it wouldn't exist. Now, we're going to calculate a few important things from this. So let's start with, what are we going to calculate? Well, we're going to calculate the total probability of a particle existing. What should the total probability of a particle existing be? Well, probabilities, 1 is 100% probability. So it'd go from 0 to 1. 1 would be what we should expect to get. Then we'll look at what's the most likely speed. What's another term for the most likely? Most probable. So that's going to be the most probable speed, then the average speed, then the RMS speed. Now, some things to notice about this equation are, what's the probability of a particle having a speed of 0? Okay? It goes to 0 at 0. So the probability of a particle having a speed of 0 is 0. Probability of having a speed that is infinitesimally above 0, yeah, that's a real number. So the speeds go from 0 up. And what's the probability of a particle having an infinite speed? It comes back to 0. We can look at this equation and say, what's the limit as v approaches 0? Well, if v approaches 0, this is approaching 0, and this is approaching 1. 0 times 1 is 0. So the equation, we can, instead of looking at the graph, we can look at the equation and see, yeah, as v approaches 0, this function approaches 0. As v approaches infinity, then this is v squared. That's infinity squared, right? And what's this? What's e to the minus infinity? 0. So we have something that is an infinity times a 0. How did we find the value when we had something that was 0 times infinity? We had to use L'Hopital's rule. So let's real quickly do that. I don't have a slide prepared for it, so I'll just do it right here. So I'm going to find the limit of f of v as v approaches infinity. So for L'Hopital's rule, you always need a fraction. So I need something on top and something on bottom. If you look at this, it's real simple to put the 4 pi v squared stuff on top. And so I'm going to put this thing here raised to the 3/2 power times 4 pi v squared on top. And then on bottom, I'll put this exponential. What happens when I put the exponential on bottom? I flip the sign. So on bottom, it's just going to be e to the, and I'm going to write it the way it's usually written, mv squared over 2kt. It's the same thing. I just like to put the 1/2 on top so you can see, hey, that was kinetic energy. Okay. So now if I take this limit using L'Hopital's rule, I'll take the derivative of the top, divide by the derivative of the bottom. So I'll take the limit as v approaches infinity of this stuff to the 3/2 power again, times 4 pi times 2v. And on the bottom, take the derivative. That means you take the derivative of the exponent and bring it down. And so I'm going to have mv over kt e to the mv squared over 2kt. Notice my v's here would just cancel. And as v approaches infinity, what's happening to the top with the v's canceling? It's a constant. What's happening to the bottom? It's going to infinity. So what does this approach as v approaches infinity? 0. Okay, so we could see using L'Hopital's rule that this equation predicts that it goes to 0 as speed goes to infinity. Now I have to point out, just for, I don't know, my anal retentive purposes, this equation is a non-relativistic Maxwell-Boltzmann distribution. If you include our concepts of relativity, one of them is that nothing can exceed the speed of light. And so the equation has to change so that the probability approaches 0 at the speed of light rather than at infinity. But as long as we're dealing with ordinary temperatures, we can use this simpler form and not have to go to the relativistic form of the equation. So I'm just pointing out this technically isn't the correct formula. It's an approximation for what we call the classical realm. The classical realm is the physics before 1905. It's the physics before relativity came around. It's the physics before quantum physics came around. because Albert Einstein gave us relativity, and as an offshoot of the photoelectric effect, quantum mechanics. He wrote 3 papers in that 1 year, and each one probably should have been worthy of a Nobel Prize. Any idea what he got his Nobel Prize for? There's only 3 options. There was Brownian motion. He explained Brownian motion. There was on a theory of special relativity. Special relativity meaning relativity that is reasonably simple for us to deal with, as opposed to general relativity, which is tougher to deal with. And on the photoelectric effect, which was saying that light behaves as a particle. What do you think? I saw one answer. Wait, what do you think, Tori? Literally no idea, just a guess. Okay. Well, other people, anyone want to, just any inklings? Yeah. Gonna go with it must not be the one that I would have expected, is what Ryan's saying. And you're correct. It's not the one you expected. It's the one that Ann knew and Tori guessed at. He got the Nobel Prize for the theory of photoelectric effect, which is what led to quantum mechanics and leads to our understanding of many things, allowing us to have things like light-emitting diodes or the CCDs that we use in cameras and that kind of thing. It's pretty important. Okay, let's move on. First of all, we're going to be doing some integrals of an equation that has the form of v squared e to the something v squared. I expect no one in here can do that integral. I know I can't, and I'm expecting that you're in a similar ballpark. So this is a paper that I handed out to you that shows us solutions. People have worked out the integrals as long as you're going from 0 to infinity. If you're not going from 0 to infinity, well, then life isn't so good. But as long as you're going from 0 to infinity, the integrals have been worked out. And so, in short, this box, right, there's text here to explain what's going on, but this box is the important thing. If I have an integral that's equal to integral of x raised to the nth power e to the minus some constant times x squared, going from 0 to infinity, then if n is equal to 0, my answer is 1/2 square root pi over a. If n is equal to 1, it's 1 over 2a. If n is equal to anything above 1, then I have a recursive function that says it's equal to n minus 1 over 2a times the integrand from, the integral result from 2 less. So if I was going to do I3, it'd be 3 minus 1 over 2a, no, it's 2 over 2a, 1 over a, times I1. So we can use this to solve all of our integrals as long as we have an integer power for that x. Now in our case, it's not truly x, it's going to be v, but that's just a name, right? The math, it's just a name that we give to a variable. We don't care what the name is so much as we care about having the form. So you have this paper. I will probably ask you, actually I have one extra. Why do I have one extra? 1, 2, 3, 4, 5, 6. Okay, who doesn't have one? Okay. Like there's supposed to be 9 people and I printed 9 of them. Here you go. So I'm going to rely on you to help me out with these integrals. we are going to start off by finding the most probable speed. So I have this function. Now notice that I've rewritten the function. I'm going to have this written on the top of each page as we go on from here. I've rewritten the function in terms of two constants. One I called A to match the formulas on your equation sheet. So that A is the coefficient of v squared. So if you look in the exponent, so if you look in the exponent, that's 1/2 m over kt is what A has to be. B is the stuff that is multiplied by v squared e to minus a v squared. So I take that 3/2 power of m over 2 pi kt multiplied by 4 pi. That's my b constant. But notice that a, m over 2 kt, if I look at b, I can see that, come on, change. If I were to take the pi out of this, that thing inside the 3/2 power would be a. So that means this thing here is a over pi to the 3/2 power. And if I take a over pi to the 3/2 power and multiply it by 4 pi, remember that's a to the 3/2 over pi to the 3/2 times 4 pi, and I'll put to the 2/2. Pi to the 2/2 over pi to the 3/2 is what? Okay, so it's 1 over pi to the 1/2. And so I took this a to the 3/2 is a times square root of a, and I canceled this to make that a 1 and wrote this as 4a, so this 4 and the part that's not square root of a, and then leaving the square root of a over pi afterward. And so b can be more simply written as 4a times the square root of a over pi. So now that I've written this in its simplest form, well, we now have f of v is equal to b integral from 0 to infinity v squared e to the minus a v squared. Oops. That was going a step ahead. I was going a step ahead. I'll do that when I get to an integral. We now have simply that f of v is equal to b v squared e to the minus a v squared. That's what we have right now. So I simplified it out. Given this relationship, how can I now find the most probable speed? Going back a step, I said the most probable speed, or most likely speed. What does it mean for it to be the most probable speed? In very simple terms. The what? Yeah, it's going to be the maximum point on the curve. Most probable means the probability is the highest. And so probability is the highest and the highest point of the curve. How do we identify mathematically where the highest point on the curve is? We do what? Critical number things. Okay. We find the value where the derivative is 0. So to find the most probable speed, I can't change colors. I hate that color. Okay. When the derivative evaluated at the most probable speed is 0. So I'm going to take the derivative and I'm going to put, instead of v, I'll put v sub p to say the most probable. and set it equal to 0. Right? Because the derivative is not always equal to 0. It's only going to be equal to 0 if I'm at the most probable speed. Now, is the most probable speed going to be the only place where the derivative gives me 0? Not necessarily. What else would give me 0 for the derivative? A minimum. So we have to check to see, is this a maximum or a minimum? So let's go ahead and do this. Okay, lead me. What do I have when I do that derivative? Better leave it like, oh yeah, you've got it written right there, the violet. Okay, so 2bv It's okay.
But anyway, negative ab squared e to the negative ab squared.
Only one problem.
Oh, yeah.
So then it would be
Minus 2 av e to the minus a v squared. What rule did he use? Somebody besides that front table, since they answered everything there, what rule did he use to find that derivative? Not the chain, the product. I've made plenty of mistakes in my life with this wrong name. I know what it is, and I use the wrong name, so I don't blame you. Go ahead.
There is chain rule.
Yes. Well, there is chain rule. You're right. Because when you do the derivative of the exponent. Okay, so we've done this derivative, and we're saying it equal to 0 at VP. So I put VP everywhere. Rewriting this, notice I have a B, a VP, and the exponential in every term. So I'm going to start by factoring that out. So I'm going to put VP times B times e to the minus a VP squared, because every term had that. And then what's left? The first term had a 2. The second one had a minus. Actually, I could have factored out the 2 now, couldn't I? I forgot that there was a 2 there. So I factored out the 2. The first term is just 1. The second term has a minus here. There was a VP here. It's better to underline that one, a VP there, and a VP squared. So I'll have this A and this VP squared. Now if I look at this, I have 3 conditions that will set this equal to 0. 3 conditions. Any one of those could be my answer. So let's start with back row Toussaint. What is the first condition you see that would set this equal to 0? So I'm looking for an equation that's not this whole thing that would make it equal to 0. This thing in the bracket? Okay. If 1 minus a VP squared equals 0, which would give me the result that VP is equal to the square root of 1 over a. Right?
Why is it VP squared in brackets?
Because I had a VP square here and a VP here. I factored out one VP, but I was left with a VP squared.
Oh,
You worry about plus and minus on that square root.
I'm not worried about it because we can only have a positive speed. We could have a negative velocity, but only a positive speed. So you're correct. Anytime you take a plus or minus, there is a positive and a negative answer. But only positive answers are possible here. Okay, so that was Toussaint's. Toussaint. Okay, next person, Michael.
if VP was 0?
That is correct. Okay, don't need to go any further with that. That math is done. Okay, and what is our third and final condition that would make this equal to 0? Okay, she's correct, but I want to back up a step so everybody makes sure they follow through to how she got to that. The last part would be if e to the minus a vp squared equals 0. And thus, if you solve that, that means that, well, if you want to do the math, take the natural log of both sides. What's the natural log of 0? It approaches minus infinity. Yeah, it's undefined. It approaches minus infinity. It's undefined. And so I have a vp minus a vp squared equals minus approaching infinity. Divide both sides by a, throw it away because it's still going to be vp squares approaching infinity. And so that gives me vp approaching infinity. It's not equal to infinity. Right. If I said it's equal to infinity, then that's denying the undefined nature.
Too many years, you're not allowed to do that.
You're allowed to approach.
You're allowed to approach. You're not allowed to equal.
That's right. And that's why there's no equal sign there. I did not violate a rule. Okay, so I have 3 possible answers. Which one do you think is the correct answer? Let's go to Hannah. And of course, not just which one, but why. Which one do you think is the maximum? Which one? Which of these 3 answers, VP is square root of 1 over a, VP is 0, or VP is approaching infinity, is going to be the maximum for my function that's in violet here and plotted? It wouldn't be VP equals 0. Jaron, what would you say?
It would be the, scroll down, the square root of 1 over a.
Okay. Jaron says it's going to be the square root of 1 over a. Why do you say that? That's correct.
Because when VP equals 0, that's the left-hand minimum. And then it's the infinity one, that's the right-hand minimum.
Okay. So those two were both minima. How can I mathematically prove it? I mean, I have the graph. I can look at the graph and say, okay, those cannot be maxima. Right? I would have accepted just, well, I looked at the graph, and those clearly weren't maxima. Yours was more clear than that. How can I mathematically check it? To make sure this one's a maximum and these two are minima. The second derivative test. If I do the second derivative and I evaluate it at each one of these values, if it's a maximum, what is the second derivative going to be? Remember my little mnemonic that my teacher taught me? So this is a maximum if the second derivative is a negative sign. It's a minimum if the second derivative is a positive sign. Now, my teacher taught me this. I was in high school. We didn't do calculus yet, so I'm not exactly sure what the context was, but I know that I was taught this in high school by Mrs. Berg. Once I understand my math better, I know that the second derivative is telling me how the slope is changing. And so if the second derivative is positive, then the slope is becoming more positive, so it's going to be going from 0 to up. And if it's negative, it's going to be going from 0 to down. So having a better mathematical understanding, this makes complete sense, and I don't need my little mnemonic pictures. But when I was in high school, I didn't have that mathematical skill. I didn't know what what a derivative was, for crying out loud. We took an advanced lab math class, and we did very small amounts of calculus in it, so that's probably where it came up. But I didn't understand an integral or derivative at that point, and so I used this so I could keep it straight. Now, Since that is our answer, let's get an actual value for it. A is m over 2kt. So that means the V most probable is equal to the square root of 1 over A. So I just reverse that, and I have 2kt over m. Now, we did not do the most probable in class. What did we do? The root means squared. And what did we find? What were we simply told and took on faith the value for VRMS was? 3 kt over m. Actually, we didn't take it on faith. We worked it out through the kinetic theory of gases. So we're going to check here and see if it comes out the same in just a moment. So those are different. They're different by a factor of square root of 3/2. Next one. Let us find the total probability. What did we say the total probability should come out to be? Yes, that's right. Everybody else with Ann? Yeah, 1. So we should have the total probability. Now I said the probability, I'm just going to put probability, of being in V to V plus dV is given by f of V dV. So if I want to find the total probability, that's the probability of being in region dV. So for instance, I could say, okay, here's my V, and the width of this will be dV. So I can find my probability of being between those two lines is f of V dV. How do I find the total probability? Integrate over the entire range. What's the range of speeds here? 0 to, yeah. Well, we're taking the non-relativistic form, so we say 0 to infinity. Yes, if we were being relativistic, we would be more accurate. So I'm just going to say my total probability is equal to the integral from 0 to infinity of f of v dv. Well, let's plug in our f of v dv, integral from 0 to infinity. I'm going to put the b outside of my integral sign because it's a constant. V squared e to the minus av squared dv. Now you have the integral table. What is this integral going to be? First, let's talk in terms of the subscripts they use. I, 0, 1, 2, 3, 4, 5, etc. From your page, what would it be? I sub 2. Because it's v squared. Because that is a 2, then that is a 2. And then we have from that table, how does I2 relate to our two starting I's? So what is n? So 2 minus 1 over 2a times I0. So I find I0 and I'm done, right? I'll go one step. I can do 2 minus 1. That gives me I0 over 2a. Okay, so now you can look in your table some more. What is I0 equal to? It's 1/2 square root of pi over a. Okay, we can put this all together now. We will have I0 is 1/2 square root pi over a. I2 is I0 over 2a. And so that's going to be changing colors. That's I0 divided by 2a. Now, something tells me we made a mistake here. I'm not sure what it could have possibly been, but something tells me that. Because I know when I practiced I came out to 1, and this doesn't look significantly like 1 to me. Right? It looks like something completely different. Oh, wait a minute. No, that's right. Oh, that's I2. I have to put the B with it. That's where my continuation is. So there's I2. So the total probability, at least I figured out before I started going crazy. Equals BI2 right there. So that's going to be, what was my value of B? It's up here at the top. B is equal to 4a square root a over pi. And then I2, 1 over 4a square root of pi over a. And now we see it is what it should be, because canceling things away, 4a, those cancel. Square root of a over pi, square root of pi over a cancel. And that's equal to 1. So my total probability is 1. Why do I do this calculation? It's a sanity check. It's a check to make sure that things are going in the right direction, that this Maxwell-Boltzmann distribution doesn't fail before we've even started. So now, let's go to the next problem of finding the average speed. Question?
The total probability, what's the probability of its existence? Is that
Yeah,
what you said earlier?
yeah. That's the probability of it having a velocity,
Oh, okay.
which is the same as the probability of it existing, right? But if you want to be technical, that's the probability of having a velocity.
You can't just sit.
Hmm?
Particles don't just sit ever. They have to move.
Well, that actually is true. Quantum mechanics says that unless the particle is completely unbounded, the universe is its oyster, it has to be moving. Which really doesn't make sense to us, right? That's why you hear people joke about quantum physicists going and arguing about getting a ticket saying, but it's not possible for me to ever come to a stop. Hence, it's ridiculous for you to make a judgment on how close was I to a stop. I suppose it would depend on your judge if he uses logic or if he says, well, golly, you got a point. But that's not my problem here. I want to find the average speed. How do we find the average position of mass if I have mass distributed through an object? Well, it was with calculus. You are right, sir. Good thing you came to the Tuesday class then. How did we do that? We called it the center of mass, right? How do we find the center of mass? Carefully. When we found the center of mass, we said the x center of mass, which would be the same thing as the average position for the mass, was equal to the integral of my probability function for the mass, which was m over the integral of dm times my position. Actually, yeah, the way I'm writing it here is not going to work out very well for me. It was integral of x dm over the integral of dm. That's what we did. we've just done the integral of the probability, and it gave us 1. What we're going to do for this is the average speed is the integral of the probability of any given speed times that speed. Actually, I don't have to put the dv because probability had the dv in it. So that's going to be the integral f of v dv multiplied by v. Now, that v is inside the integral, not outside. I usually like to put the dv last, so I'm going to rearrange it now that I've written it because I like to have the dv last. Everything before the dv is part of my integrand. Well, the dv is too. What are my limits for this integral? 0 to infinity. So now if I write this out, that's going to be b integral from 0 to infinity, v now cubed because it was v squared times v, e to the minus a v squared dv. In terms of the i's, what is this integral? I3. So that's b times I3. Well, we just need to find then what I3 is. So using our iterative relationship, or iterative, recursive relationship, what is I3 equal to? Exactly. And of course, 3 minus 1 over 2, that's 1. So that's just I1 over A. What's I1? We have that written out for us. I1 is equal to what? 1 over 2A. So putting this all together, my average value for speed is going to be equal to B times I1 over A, which is B times 1 over 2A squared. Did I do all my math right there? So I have to now put in B. B was 4A square root of A over pi. Put the 2 the wrong place. So combine that all together. 4 divided by 2 is 2. Putting the 2 inside the square root sign, what does it become? 4. We're pretty good at this math game. Now I have A times square root of A divided by A squared. If I put that all into the square root sign, it's A cubed over A to the 4th. So on the bottom, I'm going to have pi A. Or square root of 4 over pi, and then my A was my A was m over 2kt, so 1 over A is going to be 2kt over m. 4 times 2 is clearly 8. And I have my average speed is equal to the square root of 8 over pi kt over m. Now, square root of 8 over pi, how does that compare to what we found before for the average? What did we have for the average? It was square root of 2. So how do those relate? Which is bigger? What's 8 over pi? Let's make it easy and say, what's 8 over 3? 2 2/3. So this is going to be more than 2. So this value here is greater than that one. Now we had the KT over M that I just dropped off because I was comparing the differences. And so we have the average speed is greater than the most probable speed. And we actually have a mathematical relationship. If I know the average speed, I can calculate the most probable speed or vice versa. Now for our last, any questions on this? For our last trick then, let's use the Maxwell-Boltzmann distribution to calculate what the RMS speed is. So going through what we've done before, first I need to find the average of v squared. Sally, how can I find the average value for v squared? No, I need to integrate my probability function multiplied by this v squared. And so that would be b integral from 0 to infinity of, the probability function was b v squared times v squared is v to the 4th, e to the minus av squared dv. Of course, what would we call this piece right here? I4. And what should I4 equal? So if I put this all together, I have the average value for v squared is equal to b times 3 over 2a times I2. I wrote it this way for a very specific reason. We've already calculated what b times I2 was. Do you remember what b times I2 was? BI2 we already determined was 1. So I can save myself some time by saying we determined that from the probability, sum of probabilities. Saving myself doing the same work a second time. And so that means my v squared average is equal to just 3 over 2a. So that means my RMS value, how do I find the RMS? What's the 3-step process to find the RMS value? First you square it, then you find the average, and then you square root it. So I had the average of the squares here, so I have to square root this to find the RMS value. And now let's plug in values. The RMS is equal to the square root of 3 over 2, and then 1 over kt, or 1 over a, is going to be 2 kt over m. Well, of course, the 2's cancel, and that's equal to the square root of 3 kt over m. So now putting these all together, and I am simply going to zoom in now on the graph, we have found that v most probable was equal to square root of 2 kt over m. And the v average, square root of 8 over pi times kt over m. And finally, VRMS is equal to the square root of 3 kt over m. We've already looked and said that 8 over pi is somewhere just a little less than 2 2/3. So we have 2, a little less than 2 2/3, and 3. So we can see the sequence follows the way these lines are drawn. We can mathematically go through and find these relationships. V most probable is going to be square root 2 kt over m. If I put that in terms of VRMS, I'm just going to do square root of 2 divided by square root of 3 times VRMS. So this is square root of 2 over 3 VRMS. And what about the average speed? What would I have for the average speed? I know I just took it off the screen. Okay, zoom down so we can see them both. What would I have here for the relationship between VRMS and the V average? Now, our time is up, but somebody with a calculator, can you real quickly just do square root of 2/3 and square root of 8 over 3 pi, just to make sure, we're in these ballparks? Right, we've done all this work. Make sure that the answers we worked out match the answers that I had already printed. This calculator doesn't do square roots. So, you checked them both? Okay, she checked them both. They both come up. We'll go there. Have yourselves a swell day. I'll see you in lab this afternoon.
Do we need to bring anything specific to that?